Hi all, welcome to the second part of the video lecture on complexity theory. So in the first part, I tried to give you an overview about different complexity levels, particularly what is class P, what are polynomial time problems and what exponential time problems, or simply what are difficult as well as hard problems. So like that, and we saw some examples also. Okay, now let's see on popular problem which is being discussed under this complexity theory classes, that is the graph coloring problem, which you might already studied in your graph theory classes. Okay, so it is something like so basically here we are discussing an application of the same say map coloring problem. Okay, so given a map like this, and the question is like, what is the minimum number of colors necessary to color this map so that no two bordering countries share the same color? Okay, so say Peru and Brazil or something, so these two countries are sharing a border, right? So if two countries are sharing a common border, they should be given different colors, otherwise you may not be able to distinguish, right? So if you are giving same color for both this Peru and Brazil, how you will identify the boundary? So you are supposed to give a different color. So that is the application. Now you know how you can do this. Okay, so basically you can convert this problem into a graph, and where each node corresponds to a country here. So corresponding to each country here we can have a node, and if two countries are sharing a border, common border between them, then that can be represented using an edge between them. Okay, say so the approach is model the map using a graph in a way that allows us to find the answer to the question by finding chromatic number. And you know, once you get the graph, you will be finding out chromatic number, that is a minimum number of colors required to proper color the graph. So let's see what is happening, and what is chromatic number, those things are written here, and which you already know, the minimum number of colors to proper color the graph, right? So each country is being represented by a vertex, and when two countries are sharing a common border, you can see that is being connected by an edge. Now our requirement is like two countries sharing a common border should be given different color, otherwise two vertices connected by a common edge so you can model like this. So when two countries are sharing a border, they will be having a common edge between the corresponding vertices, so that the problem is like you want to give different colors for countries sharing a common border, or when it comes to the corresponding graph, you will be giving different color for the vertices having a common edge, so both are same, right? So you can solve this map coloring problem simply by mapping it into a graph and asking for the chromatic number. Now the question is, we can proceed with the finding x of g, that is nothing but the chromatic number of the graph. So now how to find out this chromatic number? So that is the question. So chromatic number basically says what is the minimum number of colors required to proper color the graph, or what is the minimum number of colors using which you can color a map, like that. Okay, so that number of colors is like our resources, and we want to minimize it. Okay, so now it is an optimization problem to find the minimum, or to find maximum. So minimization, maximization, typically they are two categories of optimization. We are trying to optimize something, right? Now as I already told you in the previous video, we can solve any optimization problem by asking a series of decision questions, right? So the question is like, what is the minimum number of colors? So instead of trying to find the minimum number of colors, what you can do is you can simply ask, given a graph like this, is it possible to proper color the vertices of the graph using just two colors? Okay, otherwise whether the graph is two colorable means, is it enough to proper color the graph using two colors? So why I am repeating the word proper color, because adjacent vertices should be given different colors. That is our requirement. Okay, or that is our constraint. So is two colors are enough? Now I don't know how you will be checking. Suppose you are doing some manual checking and you are answering like no, two colors are not enough, then I can ask the question like, is three colors are enough? If the answer is no, then I can go for like four colors are enough. Or now you surprisingly you saw like four colors are enough, then you can conclude like the chromatic number is 4. The minimum number of colors required to proper color the graph is 4, because 2 and 3 are not sufficient. Okay, so that about it. So that is how we can handle this optimization problem by asking series of decision problem. Now the second thing is how to approach this problem, whether it how to check whether a graph is two colorable or three colorable. That I already told you. The trivial or the brute force approach says that for each vertex, suppose I have two colors, try all possibility like red and green. So every vertex will be getting two choice. If there are n vertices, the total time taken for two colorability checking will be 2 power n when it comes to brute force approach. Similarly, three colorability checking, each vertex you can try three colors, right? So say red, green and black, like that. Try any one of them, then again three colors. So out of them, red, green, those combination will be eliminated. That's checking you have to do whether these vertices are connected by an edge or not. If that is the case, you will be giving a different color. So, but trivially, you are supposed to try 3 colors per every vertex. So, if there are n vertices, 3 into 3 into 3, so 3 power n will be the running time for checking that 3 colorability. And similarly, 4 colorability, we can do using that brute force approach, which will be taking some 4 power and running time. In general, k colorability checking, every vertex will be taking k choices, so the total time taken will be k into k into k into n times, so k power n. Now, instead of that brute force approach, shall we have a better technique like so is some heuristic work like that we can approach the problem. So one may wonder, like, what about the minimum or maximum degree of the graph? So by looking at a vertex with the maximum degree, if I start coloring from it, shall I get any benefit like that? So these are all different ways we can try to approach the problem, but we don't know whether these methods are going to really help you or not. Okay, so now another thing that you can ask is whether the graph is containing an embedded complete subgraph. Say complete, so you know kn, complete subgraph of n vertices, say kc, complete subgraph of c vertices. And you know what is the speciality of a complete graph? Every vertices are connected to each other, right, in a complete graph. So if you are looking at a complete subgraph which is k3 or k4, you can see that every vertices are connected to each other, so that for a complete graph of n vertices, the chromatic number is always fixed, that is n, that you know. So like that, so you can say that minimum n colors are needed because the given graph is containing a complete subgraph kn, like that. So, or if the graph is containing n vertices and I am having a complete subgraph, maybe the graph itself may be complete, otherwise a complete maximal subgraph. So typically the maximal complete subgraph, there is a terminology called a clique. We call it as a clique. So is there any clique of size, say c? So clique is nothing but the maximal complete subgraph of the given graph. Okay, so whether the graph is going to contain a maximum size complete subgraph. So such a subgraph is what we call as a clique, whether the graph is containing a clique of size c. So like that you can approach the problem. So what benefit we are getting if you have this observation that the given graph is containing a complete subgraph of size, say kc, say c vertices, I have the guarantee that definitely at least 6 colors are needed, because a complete graph, every vertex will be getting different color, right? Because everybody is connected to each other. So when I am giving one color to one vertex, all its neighbors should be given a different color. Again, if you look at a third vertex, that will be adjacent to these two already colored vertices, so you have to give a third color. Like that, for n vertices, I need n colors. You can take some example and visualize why it is so. Okay, if you are doubtful. Okay, so what is the approach? So there is the trivial approach. So the brute force approach is very tidy here, and this is on animation showing how these colors are being assigned. And for the given graph, you can see that the chromatic number is found to be 4. And if you want, you can check it yourself. So you take 3 colors and you can try to proper color the graph, and you can see that at some point 3 colors are not enough, and the minimum number of colors required to color this particular example graph is 4. Okay, so and you can see how these colors are being assigned. So for arbitrary graph, even the most efficient algorithm determining 3 colorability or 4 colorability essentially comes down to this, in the sense try lot of combination. That means try all possibilities. The only efficient approach. It is not an efficient approach actually, but this is the current best method we are having with us. Okay, so that about it. Now, if that is the case, suppose you have a general question, say k colorability checking, it can be 3 colorability, 4 colorability, etc. The complexity will be, so basically we are doing try all possible coloring, and for each vertex we will try with the k colors. So total number of possibility will be k into k into k into n times k. So if there are n vertices, so the total time taken will be some k power n. Okay. So it doesn't seem like an efficient approach, because suppose I have 100 vertices, and just for checking the two colorability, the running time I'll be taking will be 2 power 100, and you know how big is that 2 power 100, that number. So it's not at all a polynomial running time. That also we already seen. Polynomial time means the running time is some n power, order of n power some constant. Exponential time means a constant rise to n. So here it is exponential running time, right? So, and we are not going to prefer exponential time algorithm. And what is polynomial? I hope you remember something of the form order of n power k. These are all examples, and okay, that you know. Now the question is, why we hate non-polynomial running time? If the algorithm running time is not a polynomial, in the sense if it is exponential or something beyond that, we are not happy with such algorithm. And what could be the reason? Okay, so this is something again I discussed already in our offline classes and all, but again to give you a feel about it, some slightly different example is being taken. So just go through the example. So I have a TSP problem. You know what is TSP? Traveling salesperson problem. The salesperson will be starting from a particular city, and he has to visit all cities, some set of cities, and you have to come back to the original city, and one city is supposed to visit only one time. It's not so basically it is a Hamiltonian cycle problem. On the background, the cities you can represent it by vertices of the graph, and from one city to another city, if they are connected, you can represent by an edge. And basically we are trying to find out a Hamiltonian tour, in the sense we are visiting all vertices of the graph or cities of the particular area, and you are trying to visit all cities or all vertices exactly once. So it is not at least or at most, exactly once. Okay, so you are not supposed to repeat any city more than one time, and you have to cover all cities also. So, or you have to visit all cities exactly once. And the problem we have to we are given say 100 cities, so that on background you will be getting a graph with the 100 vertices. Okay, so it is a very simple graph, just 100 cities only or 100 vertices only, and you want to find out the Hamiltonian cycle. And you know that even though that is the case, the current best algorithm for finding TSP, the branch and bound algorithm or its variation, it is going to take a running time of 2 power 100. Okay, and this also under the branch and bound technique for TSP and all, we analyzed how this 2 power n is coming. If n number of vertices, here we have 100 number of vertices or 100 cities, so to the running time taken will be 2 power 100. And you know 2 power 100, how can you write it? Like it is something like a 2 power 10 raised to 10, right? So 2 power 100 is nothing but 2 power 10 raised to 10. You can write it as 2 power 100. Now yeah, this 2 power 10 is 1024, right? And that 1024 is approximately thousands, that is 10 cube raised to 10. So this will be approximately 10 raised to 30. Okay, so this value. Now suppose you are running this algorithm on a typical on MIPS processor. Yeah. Suppose you are running this on a typical processor with a speed of 1 MIPS. You know what is a million instruction per second. Every second the processor is able to handle 1 million instruction, and the question is how long will it take to solve this particular TSP tour. Okay, so you are just having a very simple graph with the 100 vertices or 100 representing 100 cities and the corresponding number of edges and all, and you know the running time is 2 power n. So here it will be 2 power 100, which is 10 power 30. And we are going to execute this kind of an algorithm having say 10 power 30 steps or 2 power 100 steps on a processor with a very good speed, say 1 MIPS. In every second the processor is capable of doing 1 million operation. Million is 10 power 6. Okay, so in 1 second it can handle 1 million operation, or for a single operation it will be taking 1 by 10 power 6, 10 power minus 6, 1 microsecond. Okay, so every operation is just taking 1 microsecond of time, or in every 1 second it is completing 1 million number of operations. So that is the type of speed this processor is having, but still it is of no use, in the sense the number of operation I have to do is 10 power 30, which is a very big number, and in every 1 second I can do only 10 power 6 operations. Okay, so the time taken for solving this 10 power 30 operations will be something like So it is not written. You can use calculator and you can find out. You will see that it is not say a few seconds or minutes or something. It will be this many days or this many years. So that much bigger running time you will get. So and you will see why it is. I just have a graph with 100 vertices. It's a very simple graph, but still the algorithm is not giving me a solution. It keep on running for days and days, maybe years and years, and after some time it may give the solution, but by that time it is of no use, right? That solution nobody is going to use, because who is going to wait for a solution which is available after say 1 or 2 years? We don't want it, right? So that is the type of difficulty this non-polynomial running times are having, or non exponential time algorithms are having. Okay, so keep that in mind. Now how can you approach this problem is like, instead of using a single CPU, you can use some k number of processors, all are working parallelly. And what we can do is the trivial approach itself we can try. So if there are n vertices in a graph, n factorial permutations are there, and you can take each permutation and check whether it is a valid Hamiltonian cycle or not. Okay, and out of all a valid Hamiltonian cycle, you can find the one with the minimum total weight, call it as a minimum TSP tour. Okay, so this is the problem, and you already know the problem also. So the thing is that instead of asking a single processor to do all this checking, why don't you use some set of say 1 lakh processors, okay, something like this, or some 10,000 or thousands of processors. Now if I have 1 lakh processor, each processor can check some subset of permutations, right? And if you can divide correctly and you can hand over to all these processors, you can see that the running time will be reduced much, maybe from number of years and years. Now the running time is reduced to say few number of days or hours, like that. Okay, so that is a very good improvement. But what we tried is, instead of using a single processor, we increased our resource or hardware. So, and we ask everybody to work parallelly in a non-deterministic fashion. So if a single CPU is working towards a goal, from the starting point, you can say it is a deterministic search kind of thing, right? So everything in every step is very clear and specific. So that's a deterministic approach. But when I'm using say 1 lakh processors and I'm asking everybody to work together and I'm going to combine the solution, it is our non-determinism, right? So non-deterministically everybody will try to reach a solution in a parallel manner. Anyway, still you can't ensure that the algorithm is going to wind up say in a few seconds or minutes. Definitely it will take more than that, but it is okay, because single processor is going to take years and years, but some 10,000 or 1 lakh processors working together, the problem is going to be solved very quickly. That about it. So you know the difficulty, right? Why we are hating non-polynomial running time or exponential running time, and always what we need is polynomial easy solutions. But for most of the problem that we are having in say most of the computational problem, you can see that they are either going with the polynomial solutions, right? So most of the problems are like like which are the problems which you are familiar, they are polynomial in nature, but there are many problems for which it is not easy for us to come up with a polynomial solution. So one might started asking questions like, why can't we seem to find a polynomial solution for certain problem? There are certain problems like graph coloring, satisfiability, etc., where there is no polynomial solution occur, right? So what about it? Shall we try for it, right? So what are the best algorithm we can come up with to solve them? In case of polynomial solution itself, there will be a number of approaches, and what is best? Again, the efficiency matters, and what are some of the properties shared by this problem? So whether these difficult problems, even though they are difficult, whether they are connected by some means. Okay, so that is also a very important question. We will see everything in detail. So to enable this inquiry, theoreticians began dividing the problem into different classes as complexity classes, say class B, class NB, say easy, hard, or in between, like that. Okay. So different classes and all we will see in the next video, but before that let's just quickly go through this different versions of the problem. Something I already discussed, what is a decision problem, something like yes or no, right? A problem for which all instances of the problem have either yes or no as the answer is, whether the graph is 2 colorable or 4 colorable, yes or no, like, right? So these such problems are what we call as decision problem. Examples are like is a given graph is 4 colorable? Does a string capital A contains another substring B, another string B as a substring, if set Y is a proper subset of Z, like that. So everywhere you're trying to answer yes or no, right? Yes or no, we don't know, that you have to verify. So such problems are what we call as decision problem. And another type of problem is function problem, the problem that computes certain value. Instead of asking yes or no, the problem is going to compute some value. And again, if the value computed by the problem is based on some optimization criteria and it is trying to minimize or maximize something, you can call it as an optimization problem. Okay, so like that, the decision problem having yes or no as a result, function problem that is having certain value, some numerical value as a solution, optimization problem which is trying to optimize or that is minimize or maximize certain parameters. And now from this point onwards, even though the original problem could be optimization or something, function problem, but we will try to see whether we can map that optimization problem into some decision problem, and we will try to solve the decision problem, or we will categorize that decision problem into different complexity classes, etc. So everywhere we will be referring decision problems only. Definitely, why not optimization problem? Because optimization problems are more confusing and more tougher, right? So once you have a solution to decision problem, using that you can solve optimization problem also. But directly taking optimization problem and work on it is not a wise idea. So always focus on the decision version and try to develop your intuition on it. Okay. Many optimization problem can be solved by asking a series of decision questions. This is what I was repeatedly saying in all previous videos and all. Instead of asking for the chromatic number of a graph, we might instead ask whether the graph is colorable or not. Something in this statement also, hope you know. By asking some question repeatedly, say some decision questions repeatedly, we can solve any optimization problem. So some other examples are like a click is something well-known application or well-known problem in the complexity class domain, and you can see that the click is what a maximal complete subgraph of the given graph is what we call as a, so it should be complete in the sense every vertices are connected to each other by means of some edges, and it is of going to contain maximum number of vertices also. So that is what we call as a click. And basically we are interested to find out the click with the maximum size, because even if you take a single vertex, that is also a click, because it is just a single vertex that is connected. And if I have two vertices and they are connected by an edge, that is also a click. I have a triangle, that is also a click. So we are interested on maximal click, the click with the maximum number of cardinality, and that is going to be a maximization problem, not minimization. That another example I discussed so far is minimization, and now we have a maximization problem, say click, finding click of a graph. Now the same maximization problem you can solve by asking a series of decision questions. Say whether the graph is going to contain a click of size at least k. Okay, so or if you want exactly that way also you can ask that, that's not an issue. But here we are asking for a maximization problem, we are asking like whether it contains a subgraph of size at least k in G. So that you repeatedly ask, and you will find out a solution for your optimization problem, optimization version. Okay, so let me take an example. Suppose I have a graph with say 10 vertices, and what you are doing is you are asking the question, does the graph contains a click of size at least 10. So for maximization problem, it is always better to start asking from the maximum. Okay, or if you want you can start from 1 2 3 like that also, but that starting from a maximum value is going to converge faster. So you can ask the question, does the given graph contains a click of size at least 10, and suppose the answer is no. Okay, so at least 10 in the sense 10 and above. So for 10 and above I got the answer as no. And then you repeat the question, does the graph contains a click of size at least 9 vertices. The original graph is containing 10 vertices only. So now the question is at least 9 vertices, whether it contains a click of size at least 9 vertices. 9 and above, already we know that 10 and above is not possible. Now suppose this also answering no, 9 and above is also not possible. And then you can ask, does there it contains a click of size. So all are decision problems only, decision questions only, at least 8. If answer is no, if it, again you ask at least 7. Suppose at this point the answer is yes. So that says that does there exist a click of size at least 7? Yes. But we already know there is no click of size 8, 9 or 10. Okay. So that says that the maximum click size is 7. Okay. So does there exist a click of size at least 7? You are answering like yes. That means the maximum click is going to be of size 7, because we started checking from 10, 9, 8 and everywhere we got a negative result. There is no such click. So the maximum click is going to be of size 7 only, right? So that is a way. So for maximization problem, typically we ask the question like at least k. Similarly for minimization problem, you will start from a smaller value. Like 1, 2, 3, 4, like that you will ask. As it is a maximization problem, we started from a maximum value. Okay. You got it, right? So as a minimization problem is something like we will take example, but you already know chromatic number and all. Okay, say TSV2 etc. So the conclusion is the solution to an optimization problem can be obtained by asking a series of decision questions. Okay, so or using the solution associated with the underlying decision problem. So that is the conclusion. And for example, if you are looking at the traveling assessment problem, which is a minimization problem, you are trying to find out the minimal TSP tour, and there you can repeatedly ask the question, does the graph contains a TSP tour of size at most k? So for maximization we ask the question at least k, minimization we will be asking at most k. You think about it, why it is working. Okay, just take example and you will understand. Yeah, that about it. It's so here what we discussed mainly is about this maximization and minimization version, and why we are hating polynomial running, so non-polynomial running, like that. Okay, yeah. Thanks for watching. So we will see more intuition into the subject in the next video onwards.